training company. David has served on advisory boards and economic growth organizations and partnered with companies to build workforce development solutions. He has a BS in mechanical engineering with a focus on mechatronics and nanotechnology. He has certifications from many major OEMs, including Fanuc, Rockwell, SolidWorks, Microsoft, and more. Following the presentation, we'll have a live Q&A with David. You can submit your questions at any time during the presentation using the chat box on the right-hand side of your screen. At the end of the Q&A, we will again be announcing 2 session giveaway winners. In addition, we'll be announcing our Control Automation Day grand prize winner, who will receive a My Palletizer 260 M5 stack, the most compact 4-axis robotic arm, plus an adaptive gripper, courtesy of our friends at Mouser Electronics. So thank you so much for joining, and with that, I'll hand it off to David for his presentation.
Hi everyone, my name is David. I'm the Director of Engineering Content for Control.com. A little bit about my background is I've done a lot of programming with robots, PLCs, and HMIs. So recently, over the past couple of years, we've been hearing a lot of talk about these things called industrial PCs. So I thought that naturally, when we talk about robotics for this Control Automation Day event, it might be natural to do a hands-on demonstration of how you would connect a robot and an IPC together for handshaking, for communication. It's a great initiative, but the more I got into it, the more I began to realize that there were a lot of complexities to this challenge. So while I still intend to provide you with a tutorial, I realized that I had to do some learning myself in order to get a little bit more experience with what IPCs were, how they work, and actually how they fit realistically into the scope of control. Now, a little bit of background on IPCs first, this idea of an industrial PC. And most of the time, they don't really look that fancy. They're just a computer that's placed into the control system. A computer, much like if you were to connect your laptop through its Ethernet port or its USB ports and connect those to various systems around your plant. Now, as you might expect, a laptop probably wouldn't be the safest choice or the best choice because it's pretty fragile. It's not really designed to be put into a control cabinet and kept there for a long time. Overheating, it's pretty fragile, so vibration might cause some challenges to it. So really the concept of the industrial PC is that it's hardened. It's built with a ruggedized case. Inside, there's the ability to take away the heat, not allow dust to get inside, and power supplies and communication protocols that are a little bit more adapted for the control environment. Now that all makes sense. The computer technology has advanced so fast that what we consider a fast PLC, for example, is nowhere near as fast as a modern industrial or residential computer, or the computers that you might find in your office. So if we can take that technology and tie it into our control system, then what we end up with is essentially a bigger, better, faster PLC. Or at least that's what I thought, coming from the background of control system technology. But the problem is, the learning that's required to begin a project is a whole lot more complicated. If we started from scratch with an operating system, say Windows or Linux, and somebody handed you that computer without any software on it, you would be required to design the software and the applications that are going to do the communication all around your plant. Now that's no easy task. I've done some programming in C++ and a little bit of work in both Python, Java, and a few other languages, but I realized that just to get a project started from scratch, there's a lot more behind the scenes work and understanding that has to happen. What kind of peripheral equipment are we talking to? What kind of application are we doing? So I decided that it was time to rely on some outside help. Some help from professionals who know a lot more about IPCs and the idea of computer science and programming than I do. And hopefully, that'll give me the building blocks that I need to start getting a better understanding of where to start with projects and how to define the parameters that are needed before I just begin opening a computer terminal and starting to type. So come on along with me. Let's go take a trip and see if we can learn a little bit more about this whole world of robot and IPC interaction. Let's go. So I'm here with Frederick Ryden, the CEO of Olus Robotics. And before we get started talking about IPC communication to robots directly, let's give us just a little bit of context on Olus Robotics and this concept of remote control that you've been developing, and it's kind of migrated industries in the past few years.
Oh, yeah. So thank you. I'm Frederick Redden. I'm the CEO of Olus. We've really been remote controlling robots for well over a decade now. I've been doing it for 15 plus years. Started out actually in the offshore oil and gas sector, or the offshore energy sector, because they do both wind and gas these days. And we were working on remote control systems for big hydraulic robots that swim down in the ocean, right? And you basically maintenance on underwater infrastructure. So from there, we actually ended up working. That was almost 10 years ago now. And from there, we went on working with NASA, went on working with a bunch of other government agencies, the Department of Energy on bomb remediation, and then a bunch of other sort of space type projects. You'll see some old press releases if you really go digging. But yeah, we were working on space station projects and things like that. But about 3 years ago, we realized that, we built really mature and robust remote control technology or teleoperation technology for robots and primarily for robot arms. And we recognized that there was a strong need. This was sort of around COVID or after COVID. We recognized there was a strong need for remotely monitoring and remotely controlling robots because, in life before COVID, you were able to always have people on site, and afterwards you couldn't necessarily do that. So that drove us to really take our rather mature technology and productize it for the industrial markets.
So that context is going to kind of wrap up when we talk about industrial PCs.
Yeah.
This situation is fairly unique for what a lot of people probably see when they think about robot to control system communication, is they just think about PLC technology. So your example in the context of the situation is more talking about using the robot to be remotely controlled from elsewhere.
Mm-hmm. Mm-hmm. Yeah, and I think the first discussion we had probably PLC versus industrial PC. A lot of if you're from the robot industrial automation world, PLC, and if you're from the software development world, PC and IPC, right? And this is at the industrial PC, it's almost where these two worlds meet, and I think it's an interesting place. There's a lot of things happening in that space right now, and basically being leveraged to build higher value functionalities for robots and automation that we just didn't see even 5 or 10 years ago. But yeah, back to the main thing. PLC is when you have ladder logic. There's often safety involved. So you need to make sure that all the signals from the robots or the cell are in the state they should be. Otherwise, there should be an emergency stop and things like that. Versus an industrial PC, it's more about traditional software development, probably not related to safety, but it's maybe crunching a lot of data, crunching a lot of robot data. Maybe it's doing advanced path planning. Maybe it's inverse kinematics planning and even computer vision. So all of that stuff is more on the industrial PC side.
So the first topic that I wanted to talk about was why. Why was the choice an industrial PC? What kind of gives that some advantages over this PLC, IPC? You were just mentioning that debate about these two, and there's certain contexts, I'm sure, that are appropriate for one or the other. So in your case, with remote control, what about an IPC gives it strategic advantages over a PLC?
Yeah, so I think for us, for remote control, there's a lot of things. Let me grab an IPC here and just kind of put it up here. We can orient ourselves. We want to do things more than having robots, right? We want to talk to robots, but we also want to talk to cameras. And now we want to crunch data in more some general sense. Maybe we need more compute power than the PLC typically has. We know that what we're going to do is not safety related. We're not going to actually act on safety signals and ensure that fences are closed and things like that. So, there's always a gray area. Sometimes it can be done with a PLC and it can be done in IPC. But basically, the further you drift away from control logic and safety in real time towards more general purpose software development, then you start talking more of an IPC.
Now, just a moment ago, you mentioned cameras. So once we start adding extra hardware, obviously the core of our discussion today is talking about the IPC to the robot. But there's a lot of other peripheral equipment here that it could potentially be connected to a PLC. I'm sure there's people that have connected cameras to PLCs and done some more creative system design, but then creativity also adds a lot of complexity and the lack of ability to maintain a PLC system.
Yeah, so let me add a camera, just kind of for illustration. We're going to put a camera up here. That is probably going to send a signal to the industrial PC. You can add a robot as well. There's going to be communication here between the robot and the industrial PC. And this communication is fundamentally no different than from what you would have with a PLC. You're going to get joint state, where's the robot at, where's the I/O doing, what's register value 5, like those type of things. It's the same type of telemetry. It might not telemetry. It might not be delivered using the same protocol. Maybe this industrial PC is running Ethernet IP as an adapter. Maybe not. Maybe it's just communicating with the regular, string socket messages with the controller. I think when you move to the industrial PC, it's sort of, you can kind of do whatever you want. It's kind of whatever is most convenient or what's available on the robot controller or the PLC or things like that. But now we can take all this data, we take the video data, we can take the telemetry, and we can crunch that. And you would see this set up in many AI picking applications. They would crunch the information from maybe 3D sensors and robots, and they would decide, okay, go to pick at XY, and you would send some sort of control command like this. What I like to do is emphasize that since this is not a real-time device, so a real-time device is when something happens, when program execution is happening as predefined, sort of deterministic intervals, right? It doesn't necessarily mean fast or slow. An industrial PC can operate very fast, but you don't have a guarantee that in clock cycle, 1,000,000,001, this thing is going to happen, right? It might be off by a millisecond or so, right? So it's not appropriate for safety, but it means that you can actually process things safely. You can send a request. So instead of saying, hey, this thing should now command the robot, I like to say it should request it from the robot. Because the robot is a real-time computer, it can handle safety signals, and it can then make the determination, is this a safe position to go to? And depending on where the robot is currently at, no safety signals are triggered, everything is green basically, it might say yes, go to XY. XY, okay, right, and it can execute that command. So versus more of a PLC, it's a real-time device, safety, it has to do with safety, it can handle safety signals. It can just say, it cannot, it doesn't even have to ask. It's just going to be the primary in that relationship, and it's just going to say, go to XY, and the robot's just going to go to XY. So that safety aspect is rather important when we talk about industrial PCs.
So you mentioned kind of that primary, secondary role, and I think that's how most people see the PLC is it's interfacing with robots and it's interfacing with sensors and solenoids. And
right.
So the PLC is a primary device, but now we've switched to IPCs. Usually, at least I kind of have always thought the opposite. When a PC is involved with a control system, is usually the PC is kind of that server, the one that everybody sends their requests to, and it distributes the information. So you're saying this has the flexibility to kind of be designed in either case. So in this case, the robot is primarily in charge of determining the safety. The IPC is simply sending a request to the robot.
Correct. So it fully depends on application, but yeah, exactly. You have that flexibility. You look at your situation. What are the safety implications of the signals going out? And you can make your determination what's most appropriate from there.
Now you mentioned data, the information being of various different kinds, including like register values, things like that. So is that pretty familiar to people who've done robot programming before? There's nothing magic or behind the scenes about this as far as the data transfer. You're still just coordinating the sending of numbers and values of registers and even bits between the controller and the robot.
Yeah, and I've seen all sorts of schemes here where people, they basically actually designate the industrial PC as a primary, and they just, all the robot ever does is goes to whatever joint position gets outputted here. And essentially there's no logic going on in here. I don't like that architecture. I think it's sort of it turns into a problem. It's more about black box at that point, and it's very hard for training even robot experts to diagnose such a system, right? So what I want is I want to actually have, logic and, in the robot controller that says, move J, set IO on. I don't know if this can be seen, but set IO on, and then we can say, okay, now, get IPC input, right? And then we can now move to that new position if we determine that as safe, right? So the difference here is I'm still handling all the logic on the controller side, but I'm getting the information that I need. And the powerful is sort of the best of both worlds, because you now have a situation where you're writing a program in a language that is fully understood both by software people and by robot engineers or robot controls people, right? And at the same time, you can have very advanced functionality in this call to get IPC input. It might not be just like, okay, copy value from here to here. This could actually trigger a thing where it queries all the cameras, it runs a bunch of calibrations, it determines which object needs to be picked at which angle, exactly how, and it comes back as a very simple, joint configuration or X, Y, Z position, right? So I love when we architect things like this, when it's not about just making it work, because you can make it work with a black box architecture, where this says, all that this would say is like run IPC, IPC program, That's typically what you would see people implement with ROS or something like that for the first time. And I think this is an architecture you should shy away from, because even though it might be easy to get it to work initially, it's virtually unmaintainable for anyone who doesn't have access to the full source code of what's running on here.
So the final piece of this equation that I'd really like to learn more about is the remote part of it. So I see we've got cameras, we've got robot, and both of those are going to be probably physical connections between the different pieces of hardware.
Yeah.
And there's certainly software layers that facilitate the communication, the image processing. But then the other piece of this remote control is you've got the IPC communicating with the remote device, the user who's on their phone in another state.
Mm-hmm.
What extra piece then is involved with this equation that makes the IPC the ideal choice for the whole remote part of what makes your solution work?
Right. So, these days when we write software that we want to run on your phone, on your tablet, on your PC, I don't want to have to worry, what's your operating system? Are you running Windows or Linux? Are you running the latest Windows and so forth? If I don't want to have to worry about any of that, I want to make sure it's a web application. It can just be open in a browser, any one of your devices, as long as it's a modern one like Chrome or Edge or something like that, right? It can be open. So what's running on here is a web server. So now, this can now be accessed through a browser. But you have to have access to this device. This is not a cloud application. This is not living out on the open internet. Most people don't want their industrial automation application to be out on the open internet. Like that's an understatement. But so let's say in the simplest case, what I would do is I would take an Ethernet cable and I would wire it up to my my tablet or my laptop or something like that, right? And now I can have remote access to this device, right? You can see what's going on. That is great if you, for instance, is using this as a data logger. You want to just kind of see what has the system been doing. Maybe you go in and run some diagnostic routines. But really, you could just walk over to the teach pendant or the HMI, and you can kind of do it from there, right? So there's something else missing to actually make this interesting. What people would typically do is there's another piece of hardware. This is typically called an industrial router or something like that. That it can be nice to sort of segment your network a little bit conveniently, but it can also provide this remote access functionality. So we have the industrial router here. And then that would be tied into maybe some sort of, VPN service, and then eventually it goes out on the open internet up here. But the key thing here now is that, many people are going to be concerned about cybersecurity. What if someone hacks it and all that stuff, right? So this is a very convenient way to maintain control. Because even though many robots need to be remotely monitored and they need to have their remote control capability, they don't need to be remotely accessible at all times. For instance, you can have a scheme where you say, hey, you know what? As long as the machine is just running as expected and there's nothing crazy going on, let's just keep it offline. But then maybe we have some issues. Maybe cycle times are not as good as they should be. Maybe there even is a fault, an eSTOP, things need to be diagnosed. You could have it automatically turn on, or you could literally have someone in the plant turn on a switch. We need help. Flip that switch, and this signal now starts flowing. And now you can have users with the right credentials using, the VPN and log in through their browser, and they can actually see what's going on. And this is really, really beneficial as opposed to like a cloud implementation where you basically have a 24/7 connection to the cloud. I don't want to badmouth cloud. It's I believe it can be done safely. I believe it can be done securely. But I also think we ought to recognize that the sensitive and valuable equipment that is being run here and the process and the value of those processes and the desire for the people to be in control and protect them. Mm-hmm. And in that scenario, this is a much better architecture because they can literally say, like, if someone said, you know what, I think the hackers are in, you can literally go and cut this cable off. If that makes you feel better, you can do that. I mean, you can also unplug it. That's more convenient, but.
And certainly that place where you just drew the line is kind of the difference between where many people's knowledge ends.
Yeah.
If somebody is more on the hardware side or they've grown up more on the control system side, then understanding the controller a little bit, but here the hardware kind of ends.
Yes.
And they don't understand as much about the VPN, the access to the internet, and therefore cybersecurity is a scary thing, but it's an unknown thing.
Correct.
And then kind of on the flip side of that, people who have understood software development then sometimes looking at the robot and understanding the signals and what causes faults and how e-stops are treated and how safety in a work cell is treated, that may be the completely unfamiliar world.
Correct.
So this line really represents the combination of both of those worlds and where that blend, I guess now they use that for the OT, the operational technology, IT, OT kind of come together right there.
Yes. Yeah, no, exactly. And it's a part of, and this is why Olus exists. We're sort of playing both worlds, but there's definitely a part of, the IT software people not understanding why it could be unsafe to, do certain things remotely. And it's a part of, like I was saying, the OT people not fully understanding how safe and secure this can actually be on this side, right? So it's just a lot of education that needs to be done. What I'm seeing, though, is big plans that I've talked to just in the past few months here. The people, I'm not going to name any names, but the people you wouldn't assume would be particularly aggressive about their IT deployments, they would be more conservative players. Even those guys had systems in place for gaining remote access, taking remote control, and doing so with secure credentials, where there's someone at the facility who is in full control of all the signals and everything that's going on here and can basically cut anyone off at any time.
Do you find that more commonality, is that because of recent threats and problems, or is that because of kind of the peer pressure? That's the way everybody is going more towards that kind of access. What do you think is kind of the driver for that trend?
The driver that I heard from one of our partners that put in one of these communication channels even without Olus, and he basically told the plant that, hey, this service that we're providing, this technology, is so advanced that we need to remote monitor it from another country. If you want us to park a person by the cell 24/7, the price is going to be this much, and the person is going to be very unhappy about their job. And versus if we can just remotely manage that, we can have experts available 24/7 for you. At some point, the value, starts outweighing the risks by 10 or 100x, and then people just kind of go for it.
And obviously, once the technology becomes more implemented, it becomes better understood. I think anything, when something is new and innovative, conservative people, which the industry is kind of full of those, tend to have a little bit more reservation towards accepting something that they don't understand.
Yeah.
But the more adoption happens, the better it's going to become generally known.
Default deny is a perfectly valid position. Make the person that wants to do something disruptive prove their value first. Right? You shouldn't start at like, hey, we have a plant, we need to get remote access. And remote access to what? We don't know yet, right? No, you should start with the value. Hey, we have this really valuable piece of equipment that can do all these things for our robots and our automation. Now, imagine how valuable it would also be if we could have remote access to that, right? So now you're starting with the value side of it. And so take some thinking about how you should actually go about bringing this type of thing into a plant. And don't start with technology. Start with the need and the value, and it's just plain old communication, honestly, internally.
So now we've kind of covered what we were setting out to talk about here at the beginning. Was really a kind of a small piece of this, but the rest of it provides context as to why you would ever want to have an IPC talking to a robot in the first place.
Right.
Would we possibly get a chance to be able to see this in action, actually see some hardware?
Yeah, we can go over and take a look at what we have over there. We can remote into a robot. We can do all of that stuff.
All right, well, let's go check it out.
Awesome.
Okay, so I can see here that we've got a FAMIC robot with all of the
hardware that's necessary, and this is the camera that's providing the remote vision access. So can you kind of walk us through what this cell and hardware setup is?
Yeah, there's just a couple of things going on here. So we have, the industrial PC we've been talking about right here. It got these nice little Wi-Fi antennas to it. In this case, we're actually using Wi-Fi for the external connectivity side. Of course, for the communication with the robot and the cameras, we're using regular Ethernet. Everything kind of goes through this switch here, because these are PoE cameras around. So sometimes we use USB camera, sometimes we use PoE. This is a PoE switch, and this is just a power supply. Down here on the floor, it might be outside the picture, it's actually the controller for the robot. So there's a cable going from the industrial PC through on the second port of the controller. So we actually have a direct communication there.
And now is that an Ethernet communication between the IPC and the controller?
Correct. So the robot controller in this case is running a server serving up the data. And the industrial PC is continuously requesting, telemetry and other things, and also sending requests for execution and things like that.
So as part of the remote control is obviously remote monitoring, and I can see one camera here, and I think I see a second one up there. But what kind of vision comprehensively do you have covering the cell?
Yeah, so one of these PCs can actually be equipped with up to, I think, 6 or 7 cameras at this point. So and this PC can also connect to up to 6 robot controllers. So that would be in a more aggressive scenario where you have maybe a lot of robots collaborating, all orchestrated by one PLC. And you need to see all different aspects of the cell. In this case, we have 2 USB cameras. We got this robot here set up doing a little game, frankly. This is actually for a trade show. And then,
by the way, if you're not going to automate, you should be going to automate.
Yeah, it's gonna be pretty cool, actually. Yeah, so this is the second half of the automate demo. And then we have a PoE camera back here. The real reason, normally we actually only do PoE cameras. The reason is because for this little game for the trade show, the USB cameras have ever so slightly lower latency, and that's helpful when you play that game. For normal use, though, PoE camera is actually the best choice because you can string the cables a lot longer.
All right, so tell me, this is the display screen for the remote operation, and I guess remote control. We can't just, like you said earlier, we can't just step in at any time and just control the robot however we want. What are some of the restrictions that you put on this for exactly what we mean? And security and safety, you certainly don't want anybody from anywhere just to be able to log on and start moving your robot and jogging it around.
Correct. So in this case, there are a couple of things going on. So on the robot controller that's down there on the floor, the robot needs to be set in auto, right? And all the safety systems need to be engaged. So we talk about safety zones. I mean, in this case, it's a small cell. You can use kind of close to fence, but imagine you had a larger cell. You want to make sure there's no one in that cell there, right? We could potentially rely on the cameras and look around the cameras, make sure there's no one in there. But cameras can have latency. They can have compression. There are all sorts of things going on. So for safety purposes, we actually want to ignore the cameras and just look at what the PLCs and the robot controllers are telling us. Like, they need to inherently be able to keep this safe even without camera input. So that means that the teach pendant that's down there behind, that needs to be off, right? So no one is, there's not a single point of control issue with someone driving the teach pendant while we're remote controlling. So that needs to be off at all times. You also need to, the motion needs to be initiated locally. And that means that the cell essentially needs to be started up while on site. So you can't just recover from a power loss, turn it on, and start remote controlling. Like, the thing needs to be initiated locally. And the reason is because that person that initiates it locally can make sure no one is in the cell, right? So once all that's been done, you can now go in and actually take remote control. This little demo cell is set up to be like a little game. So we can just push play on that program. If all the safety conditions are met, and we're now at the start of the course. In this case, I'm not going to spoil too much from the automate, but basically you're able to move. You're able to move around, and if you go off the track, you go back to the start. You have to start over, right? So there are clearly some restrictions being put into place here. But one of the things that is being shown is that in this case, we're accepting basically motions that are in the XY plane here. But if I actually try to move up, the robot will reject that motion. If I intentionally try to crash down into the track, you can look from the side, if I try to crash down into the track, and we're just a few millimeters off, if I try to crash down, it will reject that motion too. So that's an example of how we have combined remote control with extra safety restrictions to make sure that you're not causing an inadvertent mistake, basically. You can try it yourself for a little bit if you want.
Sure.
Switch to the main screen.
Switch to the top-down view.
Yeah. I think if you hold it like that, there's no glare. Something like that.
So it's pretty similar to just jogging the robot when you're doing an initial setting up of a program, which probably many people have done that before. And it feels kind of familiar to setting up that initial, the jogging in motion in that respect.
Correct. It is jogging with a lot more steps to make it safe. Yes.
Yeah, certainly. Safety is important.
Yes. That's kind of it. There's also the ability to kind of see what's going on with the IOs. See any past alerts that have been happening. So this is important for root cause analysis. In this case, it's mostly triggering alert based off of this game, but let's say you had faults and things like that, that will be showing up out here as well.
So I guess one of the big questions about IPCs is what does it take to really get into IPCs? Because, for example, I've starting as a PLC engineer for a long time. I understand ladder logic, discrete, analog inputs, outputs, those kind of things.
Yeah.
But now trying to break into this IPC world, I'm finding that there's a lot of extra knowledge that I thought was going to be a little bit easier than it's proved to be. So with you being in this world, what are some of the basic skills differences that you've seen as far as working with people who understand PLCs? Is this something that really takes a lot of a learning curve? And if so, what kind of steps would you recommend to somebody trying to get started discovering what IPCs are all about and how to use them?
Yeah, I guess the danger when you start to use an IPC, you're saying, I want to learn everything about this. You're essentially saying, I'm going to learn everything about computing. I mean, an IPC is just a regular PC, right? And that freedom can be daunting. Like, you get to choose your operating system. You're right. Is it something more like a Raspberry Pi Linux-based thing? Is it some Windows-based thing? Maybe someone has built HMIs in Windows before. Maybe, probably should start in Windows and make it Windows-based. My background is a software developer, mainly in Linux. I feel more comfortable there, but definitely a steeper learning curve, right? If you've never used Linux before, and you want to do an industrial PC with Linux, there's a lot that you might have to learn as, using the command shell and how maybe you're going to be compiling your first Linux programs type of things, right? So I think I would start, simple and small. If you're going the Windows or the Linux route, either way, maybe start in Python or something like that. Some reasonably good yet powerful beginner language, and start using it to see, can I communicate with these different devices. Python also has a lot of helpful libraries. You can go the route of using the robot operating system ROS to talk to your robots and machines. That's going to be primarily in Linux. So if you want it to work really well, it can also be, it can be a helpful prototyping tool. Just know, if you're the type of guy who really wants to get into the weeds of how do I talk to different registers and things on the robot, ROS is actually an abstraction taking you away from a lot of that stuff. They're trying to simplify it and make it quicker and easier to prototype new things. So I would actually stay away from it and go with just something standard like Python if you're starting out and you want to stay at that low level with full control of what's going on.
Yeah, and I would imagine also the encouragement there is not to go at it alone. If you have no experience at it, don't just get one and then open up a computer and just start trying to learn. Come alongside somebody who understands it and can kind of understand your application as well. Yes. Somebody who's more of a teacher and is willing to kind of help you understand the basics of a project like that.
Yeah, I think it's one of those things that just because something can be done with an IPC doesn't mean that it should be done with an IPC. Like we talked about earlier, a PLC might very well be the right tool for the job, right? And just, asking someone with experience maybe before you dive in too deep about hey, does this even make sense? And then sort of take it from there depending on what the answer is. Yeah. But then, like anything, Start small, start doing with the simple stuff, and see if you can get the data you need from your equipment and get it later to where it needs to go, and maybe it needs to be uploaded or a web server like I'm doing. But yeah, start small and kind of build it out from there.
Well, I definitely understand that encouragement because I'm kind of at that stage myself, just starting to get started with IPCs and running into some of those familiar obstacles that people with similar backgrounds in PLCs might also face. So
yeah,
it definitely is a learning curve, but the opportunities that it seems to be able to afford for control systems are so incredibly powerful that's why that learning curve tends to be so steep.
Correct.
Well, thank you very much for your time. I really appreciate it. I've learned a whole lot about the system, but also kind of the architecture of how this works.
Yeah.
So this experience has been really good for me, and I thank you for your time.
Welcome. Come back anytime.
Awesome. I'm sure I will. Thanks.
Thanks for coming along and joining me on that trip. I hope you learned quite a bit, as I did when I was up there. And as far as those hands-on tutorials and guides for using IPCs for various equipment, those are going to be coming soon, because we don't anticipate letting go of this technology or letting it fall behind. This technology is certainly going to be around for a very long time, and as far as the difference between PLC and IPC technology, it's hard to predict the future to tell which is going to become or remain the most popular in the future. But regardless of what happens, as we move forward with trying to understand this technology better, it's going to be important to have some guides and tutorials for many different brands of IPCs and different operating systems to understand how they work. So a few main takeaways from this project that I learned are: the first one is, it's hard to go into a project like this with a simple goal of like the Hello World program, where we just make a push button operate a light or a solenoid. That's quite simple in a PLC, but it's a far different story in an IPC. So we have to define the parameters of our project first. The second thing that's really important to understand about IPC technology is that it requires a lot more skills than just ladder logic technology. Coming into that myself, I figured that it wasn't going to be that difficult to learn this new concept, but there's going to have to be certain things that we pick up along the way. So based on those two things, this is no small project. And like I said, stay tuned for these tutorials, because we certainly will continue to provide more of that in the future. But for now, we've gotten a much better basic understanding of how IPCs can be used in certain situations, especially when we're involving technology that's not typically found in a normal control system. So until then, we hope that you'll stay tuned, keep an eye on control.com, and in the meantime, go build something awesome.
All right. Well, thank you, David, for that presentation. We've got a bunch of questions in our queue. For those of you in the audience, there's still time to submit more. So look on that Q&A box up to the right and submit those. David, you ready to answer some questions?
Yep, I'm ready.
All right. So the first one, I'm going to kind of hide the person's company they're working for, but where they're working says they have this system in place, and they're really just saying, I think, confirming what you found is that it's very convoluted to get this communication running and remotely connecting to a robot machine. So before I get to the question, is that kind of what your experience has been too, that that's very hard to get started? And
I think really it depends on what background you come from, because there's certain things that are built from a legacy control system environment that make things more seamless. And when we expand IPCs, since there's much more flexibility in the system, there's going to be a lot more complexity. And I think that can appear convoluted based on the number of people that are helping to develop a project and what their background is. So maybe we can get into the specific question there, and maybe that'll help clear up some details.
yeah, so then that specific question is, are smaller business entities more interested in this service now that and are they able to easily implement this setup as well as maintain it? I think they're getting the fact that not just getting it started, but how do you maintain that? And we're used to having to maintain our Windows systems and get updates and all that kind of stuff. So does it require that ongoing maintenance?
I think just like with any control system, absolutely it would. And not only ongoing maintenance from a control system perspective, but also from the IT perspective. And I think that's the main thing that differentiates this between the traditional PLC technology, is that it really doesn't focus on the hardware anymore. It focuses on the software. So when the question is whether small business entities are more interested in this service now, if it's a small business that has a little bit more of an adaptability to computer programming or computer science type of applications, then this technology is probably going to be very appealing, because it's going to be programmed in an environment that the employees are more familiar with. Whereas on the other hand, if you look at a small machine shop, for example, where the typical skill set is more around the discrete hardware and the more PLC-based control technology, then this kind of IPC thing would be extremely difficult to just dive into and adapt to, kind of like I did with this project, assuming that the technology was going to be easy to pick up. There's quite a different skill set that's required. So I think it really depends on the small company. I think there are definitely small companies that are going to really run with this technology because they can be more flexible than a big company, but they also might be limited by the skills that they have in the team.
Okay. This question is interesting. Is how is an IPC better than a dual core PLC that has a Linux core?
Yeah, so that's actually, if there's a specific example of that one, actually, that was just discussed on one of our previous sessions. Arduino has made a professional series, and one of their controllers actually has the more PLC traditional, it's programmed in a ladder logic IDE, but it also has this Linux core that can do communication with like an IoT, more IoT environment. So it really has both wrapped up into the same machine. Now, whether an IPC is better than that or not, I think that remains to be seen. And it still at this point, like we mentioned during that interview, is there are applications where the PLC is probably better suited for the IPC in a small situation, one machine where there's only discrete IO or maybe some analog IO and some simple control logic. I think those are always going to be more suitable for a PLC. And so that's why some companies have developed this dual system. But using an IPC then is usually reserved for larger scale systems where you need to connect more non-traditional equipment, or you're going to have IO that's more on a network rather than locally connected to it like in a PLC environment.
Got it. And I think what your answer there kind of goes into this question and another one we have a little bit later, but it's what IO systems are available for the IPCs, or do you still need to have a PLC for those discrete IO? And I think the question in one of the later ones that I see here is do you still need both, basically?
Possibly both. I think it's more situation based. So as far as addressing this specific one where it says what IO systems are available for IPCs, I think if you look at distributed IO in a PLC system, that's sort of where this IPC connection is going. So distributed IO basically means that you have a central control system, usually a central PLC. It has an Ethernet network adapter, and then that will go to all the different control cabinets on different machines, each of which will have an Ethernet bus adapter that has the local IO, the actual discrete inputs, the relay outputs, the analog and RTD inputs, the things that actually collect the data and control your machine. Those are connected via Ethernet. And those can certainly be connected to an IPC via Ethernet. Sometimes those will have a Modbus communication. That's a more industrial communication protocol. And pretty much every IPC that I've ever seen has the ability to use RS-232, RS-485, Ethernet, Modbus TCP, Modbus RTU, all those traditional ones that industrial networks rely on for all of that remote and distributed IO, they are designed into the IPCs. So that distributed IO, usually connected with an Ethernet cord so that it can get a little bit further reach. That's going to be what gives the IPC its ability to work with the machine level devices.
So then based on what you learned, do you think that the IPCs and the PLCs are kind of geared at different applications or even maybe different layers of what's going on in a factory?
I think that is true. And I think that for two different reasons. So first is one requires so much more development time for a simple application that a PLC is probably more appropriate. It has all of the tools automatically built in, all of the probably local IO points that just make it much easier for that application. The IPC, if you intend to make a much larger system with things that don't just include IO devices, but like the webcam, the connecting to a web server, those kind of things, that's a scale of a project where IPC might be more appropriate. But also there's another factor here that is about troubleshooting. And having worked with both PLCs and having done quite a bit of work with computer programming, PLC and ladder logic still creates an environment where technicians can easily track down problems by looking at a computer monitor that has the logic natively running on it. So when we look down at that field level environment where in the middle of the night, a system goes down and we need to find out which sensor is not responding when the item goes in front of it, that's immediately recognizable in ladder logic, and sometimes can be a lot more confusing in a more traditional computer programming environment. So IPCs versus PLCs, there's the development conversation and the capability, but then there's also the troubleshooting conversation. And that's why I continue to think that while they both have a lot of power, PLCs probably are not just going to disappear. But I recognize that a lot of people will have varying opinions on that. And I can't tell the future. So I'm just excited to see where things develop in the future to blend the more complex things with the ease of troubleshooting.
Gotcha. All right. This question is asking are all IPCs programmed in Linux? Because that's all I have seen.
And I think that could kind of be read as programmed in a Linux environment or on a Linux platform. And there are a lot of IPCs that can be purchased with either a Linux operating system or some derivative of Linux, but then also Windows. And I think the reason that Linux is used so much more frequently is just because of the flexibility of the system, the ability to customize it and make it your own. Nearly every major manufacturer of control system technology, if you find a big company that makes PLCs, there's a good chance they also make IPCs, and their operating system will be highly customized to their system. And it will have applications that you can purchase or download that play well with its variable frequency drives, with its remote IO systems, with its HMIs. So I think that's why Linux is so much more common in this environment, because it is so flexible, and that's what it was designed for in the beginning.
All right, this question says, what's the IDE, that you normally use for programming an IPC, and does it use IEC 61131 languages?
I think that kind of goes back to understanding what an IPC is. And an IPC is a computer with an operating system. It's not something that you would plug into a computer and upload a program to. So when we think of IDE, we'd open up our laptop, open up the IDE, the Rockwell IDE or the Arduino IDE or the Siemens PLC IDE, and then we would design our project, and then we would load it into the controller's memory. In this case, all of the programming is done directly on the machine. So we don't use a preformed IDE. We have to kind of create our own programming environment. We write the scripts, and that's why he mentioned in the interview, starting with Python, learning how to develop a project and run it directly on the machine rather than using an IDE. I mentioned that some of the manufacturers that make IDEs, they'll design their own apps. I guess that kind of makes it feel like a smartphone. You get a smartphone with Android on it or an iOS, and then you start loading in the apps that you want to control the things that you have or that you need. So in that sense, the IDE is a combination of different custom applications, and that's kind of the reason why the learning curve is so extreme for these machines.
And with that extreme learning, this last question feeds perfectly. Are there any tutorials online for making basically the hello world kind of project for an IPC? So something to help you just kind of get your feet wet.
Yeah, I guess that's kind of the whole reason that probably a lot of people are here today, is to see how do we get started with that project. And I think probably the best recommendation for getting started with a tutorial is on a simple industrial PC, or really we can take the industrial part out of it if that's not what you need to learn on. You don't need something that can withstand negative 40 degrees Celsius if you're just learning at home. So what I would recommend is something like one of the Raspberry Pi computers. It's programmed in a Linux environment, and you have the ability to pick up those basics, but you do so in an environment where there's thousands of available support topics online, an environment where people can help you learn, and you can track down a lot of resources. Then you can start getting to the more specific applications, or choosing an IPC brand that might fit your application, and you're already familiar with the steps that you're going to have to take. I think that's taught me more about programming in these environments than anything else, is some of these smaller open source boards that use a similar environment, but provide you so much greater of a community to learn from. I think that really is the best way to learn anything, is to get into that community that can provide you with the support to answer the questions when you start getting frustrated with running into dead ends all the time. That can be really frustrating.
Yeah, I think that's a great question to end on, and it happened to be our last one. So thank you again, David, for that presentation and that great discussion during this Q&A.
And thank you. And thank you to all of our viewers here for Control Automation Day. We've really enjoyed it, and we hope you have too.
Yeah. Before we wrap up, I'd like to announce our giveaway winners for this session. 2 winners will receive an event t-shirt and 6-in-1 multi-use screwdriver, courtesy of Mauser Electronics. Congratulations, Brian B. and Ken White. And now we get to announce the winner of today's fantastic grand prize, a My Palletizer 260 M5 stack. This is the most compact 4-axis robotic arm. Plus, we throw in the adaptive gripper, courtesy of Mauser Electronics. Our grand prize winner is George Shapiro. Congratulations, George. We'll be in touch with our winners after the event to ensure we have the information we need to send you those giveaway packages. On behalf of Control.com, EE Tech Media, and our event sponsor, Mauser Electronics, I want to thank you for attending Control Automation Day 2024, helping to make it a great event. If you missed any of the earlier sessions, they will be available on demand. I hope you join us again next year as we continue to bring you the best content from the world's most interesting companies. In just a moment, you will be redirected to the event landing page where you can view the Control Automation Day exhibitor booth pages and access other great content.